Hi, today I have brought you a very interesting programming question. Maybe it could be the next question that could be asked in your programming interviews. And it's also a good challenge for you to just test out how good are you in problem solving. So the problem is you have given two linked lists. The two linked lists are merged together and you have to find the merging point, the node where the two linked lists merge. So, okay, if I pictorially represent the two linked lists, they would look something like this. So this is the first linked list, probably a second linked list L1, linked list L2. So these are the two linked lists. So the first one goes like this and the second one goes like this. Okay, though these two linked lists meet at some node, they merge together at somewhere, and your task is to find this node. The first solution one can imagine is like take a one node at a time from one list and probably compare it with every other node from the other list. So we compare, we'll take this node first and from this list and we'll try to match. We'll take every node from the second list and we'll try if they are same. So okay, they are together, they are same, these two are same, no. Are these two same? No. Are these two same? No. Are these two same? No. And then again we'll move to the next node of the first list and we'll repeat the same process. Are these two nodes same? No, no, no. Okay, take the third node and then are these two nodes same? No, no, yes. And then we get the node. So this is the trivial, the basic solution, but we'll still try to analyze it. So yeah, we can assume the lists, the number of nodes in the first list is n and it's an n. So these are variable. These are actually the scale of the input. Okay. So we have to analyze our solution in terms of this m and n, how efficiently. I think for every node of one list, we have to compare it with every other node of the other list. So the time complexity for this approach would be something like m into n. And the space complexity we talk about, that would be, we don't need any extra space, we actually are just compare on the input data itself. We're not taking any uh, major space, I mean in terms of m and n. So, okay, so that was the approach, the first approach, approach number 1. So now the question the interviewer may ask you, can you think of some better approach, maybe better in terms of time complexity in this case. We cannot have a more optimal than constant, a bit of constant, right? So, what can I do? Uh, can you think of any such approach? Probably using some other kind of data structure, like stack or something. Yeah, we can do that. So we could solve the same problem by using a stack data structure. So we can solve the same problem using a stack data structure. So how we would do that? So assume something. I would number these nodes so that I can explain the solution. Suppose so 1, 2, 3, and 4, 5, and 6. Okay. The first thing is that I would traverse a single list at a time and would push it into a stack. So probably I would do something like this. So I would take a stack S1 and I would start pushing those nodes as I visit them. So 1, 2, 3, 4. Now I will take another stack S2, and would try to push the elements from the second list L2. So it will be 5, 6, 3, and 4. That the top elements in this case are similar, and they will be similar. Okay. So yeah, so would try to pop one by one the pairs of the top nodes from the stacks S1 and S2 at a time if they are similar. So 4 and 4 are similar, so we'll just pop them out. Then we are at this node, and they are also similar. We pop them out. Then we come up the other. We come here 2 and 6. Oh, they are different. So they are different means the last popped one, the previously popped one element was the merging point of the two list. You got the solution? So with that approach, we have approach number 2. How much time we are taking? So to push a list into a stack would be a linear time complexity. So we will be of m for this, there will be of n for this, and to process that stacks together, it will be again same. So the time complexity of this solution will be big of m plus n. Or if you assume m and n are like almost of the same range, then we can even consider it as the range of big of just n, and for this will be a big of n squared. But yeah, so and time space complexity, we need a space very much similar to big of m plus n, because we need a stack for that, right? We wouldn't need a stack for that. So yeah, so approach number 2 is better in terms of time complexity, and it's far better. Space wise we are using extra-place, but most of the time we are giving the first priority to the time complexity of the solution. So yeah, we can think of a solution where probably we are taking much more or much less space in probably in this case, so that we have a better solution, even better than this. So can we come up with a solution, another approach which is even much better than approach number 2? Probably it will be a homework for you. Just try if you can do, or Google it if you can find the solution that way.